Welcome back. Are boys stronger than girls? Are girls smarter than boys? Is there a difference in how identical twins respond to a given stimulus? Does a diet really result in the after weight being less than the before weight? This unit picks up where the last one left off. Hypothesis testing for one sample merely allows you to compare a sample to some hypothesized value, like is the average gas price in your city really $2.75? And it's based on the supposition or history or some other source. More commonly, we compare two or more groups to each other, and often without a preconceived notion as to which group might be greater. The ability to make comparisons between groups will bring analysis to a deeper, richer level. There are many different hypothesis testing techniques covered here, but once you have a grasp on how basic hypothesis testing works, it'll seem repetitive in so many ways, making it even easier for you to focus on the nuances. So come in and explore.
In this unit, we're going to be covering hypothesis testing when we have two or more samples. In the last unit, we looked at the basics of hypothesis testing and addressed tests where we just compared a single sample's mean or proportion against some norm, historical value, or something we just theorized. But now, what if we have two groups that we want to compare to each other, or even three or more groups that we want to compare to each other? Well, that's what we're going to be addressing in this unit. One of the more challenging questions that people often encounter is figuring out what's the correct statistical test to use. And you have to ask yourself several questions. In the last unit, we only had two possibilities, a one-sample test for means and a one-sample test for proportions. So if you're dealing with a mean, it's one test. If you're dealing with a proportion, it's the other test. That was pretty clear. But if you have a word problem, a situation in front of you or whatever, you have to decide a lot of things before you can get to the point of figuring out that one test. So we are adding another level of complication because we're going into different scenarios here. 4 questions that really will help to decide what's the right test. Well, first one, what's the level of the measurement in the variables? Your variables can be nominal, ordinal, or scale, which is interval or ratio. There are some tests designed for nominal variables. There are some that are designed for the interval ratio. There are some that are designed for combinations of the two. So you have to ask yourself, what are the variable types that you got? Like in the one sample test for means, we had a single sample and we were computing the mean of a scale variable. In the one sample test for proportions, we had to compute the proportion of either a nominal variable or possibly an ordinal variable, but certainly not a scale variable in that case. Second question we ask is whether or not a parametric test can be used. If you remember, a parameter is what the measurement of a population is. When we say parametric test, we're talking about like the two tests we did last time, the hypothesis test for means and proportions. They're parametric tests because we're dealing with population parameters. There are tests out there that are what we call non-parametric because we don't involve means and proportions and whatnot. We are having to take an alternate approach. That usually has to do with the fact that our data is not normally distributed and we have some other violations of assumptions that are critical to us using those tests. It doesn't mean we can't do anything on it. We just have to take a different approach. Sometimes our sample size is just way too small for us to deal with, and there's nothing wrong with that. So these alternate approaches, they may not be as powerful, but the nice thing is they really don't have any assumptions to worry about, so we can just move on and use these alternate options. For the most part, we're going to be addressing the parametric tests in this course, but you do have to ask yourself whether or not you can use it. Third question, how many samples are involved? When there was only a single sample, we used the two tests that we addressed last unit. If there's two samples, we have another 3 different tests that we can use for parametric and several for non-parametric. And if there's 3 or more, we have another classification of tests. So you have to ask yourself, am I comparing men to women? That's 2 samples. If I'm comparing people who have full-time jobs versus part-time jobs versus being unemployed, that's 3 samples. So 3 or more is one group, 2 is one type of grouping, and a single sample is another type of grouping. And then the last question you'd have to ask is, if you have 2 or more samples, you'd only ask this question, is the data dependent or independent? What I mean by that is there a linkage of values from one variable to the next? Like if you were looking at data for people who were dieting, you would basically be looking at what we call pre and post data, a person's weight before and a person's weight after. And you would be linking the person's before to the person's after, a one-to-one matchup of data from two different variables. That's what we call paired data or dependent variables. On the other hand, if I just had, here's my daytime class and their exam scores, here's my nighttime class and their exam scores, I have two completely independent groups. I'm not going to match Mary in one class with John in another class just because alphabetically they're the fifth person down or something like that. You don't do it that way. They're two independent groups. There's no linkage of data from, one person from one to one person from the other. So once you've answered those 4 questions, we could figure out what the right test is. In this unit, we're looking specifically at cases where we have 2 samples. First, I'm going to look at ones for independent samples, then I'm going to look at ones for paired or dependent samples. So, the t-test for independent samples. Suppose you wanted to compare the number of push-ups, sit-ups, pull chin-ups, whatever, that a man can do versus a woman. I would take a group of men, have them do whatever exercise, and compute the mean. Have the group of women do the exact same exercise, and take the mean from the men's group to the mean from the women's group. I have 2 independent samples. I'm just matching up the data from one to the data from another. There's no individual linkage. It's not like I'm comparing a person's math SAT to a person's verbal SAT. It's the same person with 2 different scores, but they're linked by a person. So it's the same person with 2 different scores. That is not independent. Even though they're 2 different tests, that's not independent. Independent, you have the same measurement in 2 different groups, and there is no linkage between those groups. You have 2 variables here also. One variable, the dependent variable, is the scale variable that you're computing. So if I were looking at, for example, number of sit-ups that a man versus a woman could do, the number of sit-ups itself is the dependent variable. It's a scale variable, and I'm going to compute the mean for the men and the mean for the women. The second variable, it's not men, it's not women, it's gender. So the second variable is gender. It's a nominal variable with 2 values, the value of men and the value of women. So we have our scale variable, which is the one we're computing the mean off of, and the nominal variable from which we derive our 2 subgroups. And each of those subgroups has a value, but the variable itself is gender. So I've got 2 variables accounted for, nominal versus a scale. The example I've got here on the screen shows, what if we looked at SAT scores, SAT math scores, for high schoolers that were schooled in a classroom versus those who were schooled at home. So homeschoolers versus traditional students. And I took a sample of 25 homeschoolers, and they had an average SAT score of 545. And I took another sample of 30 traditional students who had a mean SAT score of 490. This is all fictitious, but just want to make an example of it. I want to compare the 2 groups to ask whether or not there's a significant difference between those 2 groups. I don't expect the 2 groups to be exactly the same. The odds would be very slim that you would come up with the 2 groups having exactly the same mean. And being slightly different, that doesn't necessarily mean much either. You want to know whether or not the difference is big enough, based on the sample size that's in front of you, to be able to say, oh yeah, those 2 groups are definitely different, and it's not some random chance thing. There's definitely something to this. So you load the data. It doesn't matter which group goes on the left and which group goes on the right, as long as you're consistent. So I put homeschoolers on the left, traditional on the right. As long as the 3 numbers below the homeschoolers belong to the homeschoolers and the 300 traditional belong to traditional, I'm fine. If I flip-flop the columns and put traditional on the left, not a problem. This works either way, as long as you're consistent about how you load the data. The null hypothesis here is there a difference, basically, between the mean SATs for the 2 groups? So the formal way I might write it is the mean math SAT of homeschoolers equals the mean math SAT of traditional students. And the alternate is the opposite, which is to say that the mean math SAT of homeschoolers does not equal the mean math SAT of traditional students. I'm not picking a direction up or down. I'm just asking, is there a difference? When I'm testing if there is a difference, I am doing what's called a two-tailed test. Okay? In the one-sample hypothesis tests, we just said the mean of the sample equals a number. In the two-sample hypothesis test, we're saying the mean of sample 1 equals the mean of sample 2. And the alternate is the mean of the first group does not equal the mean of the second group. So in this particular case, I have a two-tailed test. Once you've figured that out, everything else is pretty much the same as it was for one-sample hypothesis testing. Since we know this is a two-tailed test, we would drop down to the row for two-tailed, go across, our p-value is 0.0473. What that means, to refresh your memory, is that if there really was no difference between the two groups, the probability that you would end up with results like this, just by random chance, where the homeschoolers were 55 points ahead, by random chance for that sample size, is 0.0473. There's a less than 5% chance that you could have randomly gotten those results from two groups that were equal. Well, that's not very large probability of that happening. Since it's such a slim chance that could have happened, we would say reject the null. Basically, we're comparing the 0.0473 to the 0.05 significance level, and since it's lower, we say reject the null. Therefore, we can conclude a difference in the mean math SATs for the two groups. Now, if you had an inclination or reason to believe that one group would be better than the other, and we do have some in the sense that there's so much published about homeschool students doing better than traditional students, fine. Whether or not you believe it is not the issue. It's what you're testing. So someone theorizes it, says it's true, and you say, I'd like to test that. Did the homeschoolers have a higher mean performance overall than the traditional students? Well, since the homeschoolers are in the first column, they're represented by the mu with the number 1, and traditional is represented by mu with the number 2, since they're in the second column. I am essentially asking if the mean for group 1 is greater than the mean for group 2. Well, if you take a look under the upper tail test, it says the alternate hypothesis is mean 1 greater than mean 2, or mean 2 less than mean 1, which is the same statement in reverse. That's exactly what I'm asking, is group 1 greater than group 2? So we know it's an upper tail test. Had we asked if the homeschoolers do worse, we'd be asking if mean 1 is less than mean 2, and that would clearly be a lower tail test. So in this case, we are clearly doing an upper tail test. So you'd say, fine, go across, p-value is 0.0235, which is less than 0.05. You would reject the null, and you would conclude that homeschool students have a significantly higher mean SAT score than the traditional students. So it appears they do better on the exam. This isn't a forum for you to go into the, obviously they have parents who care about them more, obviously the teachers in the schools aren't paid enough. We don't know any of it. We really don't know. It's a random sample, and that would be further research. You can only conclude within the scope of your study. You found there is a difference. You're done. The next person down the line can say, I want to do a research study to explore why there is a difference. Then they're going to have different hypotheses. You're only testing that there is a difference, or that one is greater than the other. So we see how we can address a comparison of means between two independent groups. Well, what if the data we're looking at isn't scale, but it's categorical? We want to measure proportions. What percent are smoking? What percent wear glasses? What percent, whatever it is that we want to test? Well, we can do that. What we're actually going to do now is look at comparing the proportions of two groups. So suppose we wanted to compare whether or not those getting an MBA fare better in the job market than those without an MBA. So we look at people who graduated from an MBA program versus those who have not graduated with an MBA, and they've applied for positions. Who's getting a response letter for an interview or whatever? And suppose we have 100 MBA grads who applied, and 56 got a reply back. Yes, come for an interview. And we had 200 without an MBA that applied for these different types of positions, and 90 got a call back. Is there a significant difference? Now, in this particular case, you would have reason to pick a direction. I don't like to tell people find a direction to pick, even though picking that direction does lower your p-value typically and may help you reject the null, which it's nice to be able to say, look what I found, but you don't do it willy-nilly. You do it because you have reason to believe it. Well, if you've been sold on get an MBA to help you get a better job, then you would expect that to be the case. So let's look to see if it's the case. Once again, this is fictitious data. So we had 56% of the MBA students who got a response, 45% of the non-MBA students who got a response. Don't jump to conclusions and say, well, 56 is a lot bigger than 45. So remember, you can't do that in a vacuum. It could be based on a very, very small sample. The reality is, if I used only 9 people, 5 out of 9 getting a response from one group would be 56%. 4 out of 9 from the other group would be 44%. Gee, that's not really a big difference with 9 people, but the 56 and the 44, they really sound like a monstrous difference. Yes, they do. You need to look beyond just the proportions. It's the proportion and sample size combined that really tell us something. So we want to know if the proportion of MBA grads who get a positive response and applying for a senior managing job is no different than the proportion of non-MBA grads versus the alternate. We want to know if the proportion of MBA grads getting a positive response is actually greater than the non-MBA grads. We're clearly testing if one is greater than the other. This is a lot like the two-sample test for means in the sense that I've set up 2 columns and deciding if it's upper tail, lower tail, or two-tail works the same way. But what we're counting here, there's no means, there's no standard deviations, it's just sample size and number of successes. And remember, successes here are how many meet the condition. Since I'm calculating how many got a response to the job, that's a success in this case. So I load the data appropriately. Since I've got MBAs in group 1, that's proportion 1. I'm testing if the first is greater than the second. That makes this an upper tail test. P1 greater than P2. Once again, I could have flip-flopped it. If I put the non-MBA in the first column, it would have then become a lower tail test, and you would have noticed the p-values actually shifted accordingly, so you'd get the exact same answer. Just be consistent. Well, the p-value for this is 0.0362, which is less than 0.05, so we would reject the null, and then we would conclude that, yes, MBA grads have a greater success rate in getting the interviews for senior management job opportunities than do non-MBA grads. It really is as simple as that. And it's a perfect test for categorical data, nominal data. Even if you had scale data, if you were able to convert the scale data into categorical, like, for example, if you took ages and said, I'm going to use my pivot table and group it and say over 40, under 40, you've just turned it into a category. You don't want to look at the exact ages, but you want to do something like that. And sometimes it's appropriate to do things a certain way, to group raw data into categorical values. That's fine in some cases. I don't like losing the actual data because a lot of times it's a lot more powerful and necessary, but sometimes it actually fits. But basically, clearly, as long as you're comparing 2 independent groups, if you're comparing the mean of one group to another, it's the test of independent samples. If you're comparing the proportion of one group to another, it's the test of proportions. Now, what if we have these two samples in which they're actually linked? I'm not just taking a mean of one and a mean of another. There's actually a linkage. Like they pointed out, the person's SAT math and that same person's SAT verbal. I'm linking that person's first score to that person's second score. Whatever, it doesn't matter that one was taken the same before the other, after the other, same time. I mean, but it's the same person's 2 tests being linked together. Or the most common example, a person goes on a diet, and I've got all of the participants' weights before and all the participants' weights after. I'm going to compare each person's before to their own after and link them together. What you'll find, interestingly, is that you're more apt to get significant results with these than you would with the independent samples, even with a small sample. With independent samples, we're computing the mean and standard deviation of each group. Well, one problem that can exist is that the spread of the group can be so big that the other group has to be way off before you even can say it's a significant difference. Now, if I had, one group of scores or weights or whatever with a 50-point spread, the other group, and I'm comparing it to another group that's got a 40-point spread, let's say, the 2 groups have to be really far apart for us to say there's a significant difference, because what happens is when you take the mean plus or minus that margin of error, basically, like a confidence interval, and you take the other group, that plus or minus the margin of error, the only way the results show up as significant is if the two intervals do not overlap, which means that the one group's lowest point, in the interval has to be greater than the other group's highest point. If I wanted to know, for example, if I was looking at the mean number of sit-ups or push-ups, let's say, that a man could do versus a woman can do that's applying to get into the military. And so we have two overall physically fit groups, but the overall average for the men was, let's say, 70, with a standard deviation of 20. And the overall average for the women was, let's say, 40. Well, one problem is after I take the mean and do plus or minus a margin of error using my confidence interval, I do the same for the other. It might be that on the men's side I've got 70, give or take 15. So that, so I'm going down from 55 to 85. On the women's side I've got 40, give or take 20. So I'm going from 20 up to 60. Well, the problem is the 60 on the high end of the women's is slightly over the 55, which is the low end of the men's. And even though it's like, my God, 70 for the men, 40 for the women, that's a big difference. Yeah, it is. But when you factor in those margins of error, all of a sudden, they're overlapping. And you go, how on earth could it be that far apart and still not be a significant difference? That's something that does happen, which is also why a lot of people doing research will often limit what goes in their sample. They do certain studies and they might disqualify people because they're out of their range. They say, well, we want to keep it to this range because we want to keep that spread as tight as possible. That way, when anything significant happens, we can report it as a significant result. The movement around really makes a difference. Kind of like weight loss when you think about it. If your weight is kind of going up and down 2 pounds over the course of a day, you might go up 2 pounds, you might go down 2 pounds because of eating and walking and sweating and whatever. Because of that variability, you won't really notice when you've lost a pound. You won't even notice when you've lost 2 pounds. You're not going to brag to the world, this diet's working, I'm down 2 pounds. You won't notice it until you've lost more like 4 or 5 pounds. Because then and only then are you certain that the highest of the high is lower than the lowest of the lows from the other one. You can really say there's definitely something here. Whereas, if you have a small child at home and you noticed your child's weight dropped a pound, you'd freak out. I mean, when you have an 8-pound baby who suddenly is only 7 pounds, that 1 pound difference is monstrous. Because their weight doesn't fluctuate more than a couple of ounces, 1 pound is significant there. So researchers will often purposely rig the study, and it's not illegal or unethical to do it. They will just limit the scope of their data so that there's not much of a spread so that they can notice bigger spreads. What they have to be careful of that is when they're doing their write-up, it may be that what was true as a result of their study is only valid for people in that group. That maybe we tried some special diet pill or whatever and we found, hey, it works, we got significant results. But you've excluded anyone over 250 pounds from the study. We don't really know if it works for that group. It might work really well for those under, but not over because they have other complications. So you have to be careful about your conclusions. But they might turn around and say, we'll do another study for only people in this range and another study for only people in this range. And that's not uncommon because the spread can really mess with you. Well, when we have dependent samples, one great thing about it is that it doesn't matter what the spread was like because we're not analyzing the spread of the data. We're analyzing the before versus the after, or the group 1 versus, the value in group 1 versus the value in group 2. Person's math versus a person's verbal SAT, whatever the case. We're linking the data and comparing them. So if a person's weight before the study were, let's say, 160 pounds and then afterward was 150, we are not going to use the 160. We're not using the 150. We're analyzing the minus 10, the fact that the person lost 10 pounds. So all the numbers we're actually analyzing is a bunch of very small positive and negative numbers. He gained 2. He lost 10. He gained 3. He lost 12. We're analyzing those numbers. In addition, even if the sample size is relatively small, if a preponderance of them move in the same direction, it'll show up as significant. So, yeah, we only had 10 people in our study, but 9 of them lost weight. That's a lot. Even if they only lost 1 pound, 9 people losing weight would show up as significant in a paired samples test. The reason being is if everybody did their normal routine and you just weighed people without them planning to try to lose weight for a weigh-in or anything like that, you would find some people's weight would go up, some would go down, some would stay the same. It would just be normal fluctuation. If these people are on some special diet and the goal is to lose weight and a large majority of them move in the same direction, even only slightly, the likelihood that 9 out of 10 people all lost even a pound says something's going on. The fact that they're all moving in one direction makes you suspicious, and that's what this test is actually looking at. It doesn't matter that it's a small sample. It matters that you've got the data linked together, and by the way, make sure you enter the data correctly. It doesn't matter what order you put them in, top to bottom, but whatever goes in the first column, its partner had better be in the second column. So the two are matched together. The before weight versus the after. A student's SAT math versus a student's SAT verbal. A real common group of people to use for a lot of research are identical twins. Because they know identical twins share so much, the same DNA, the same household, typically similar diets, and so many other things, that it's almost like testing the same person for their purposes. So researchers will often beg identical twins to volunteer for some of these studies, or they pay them some small amount or whatever, but it's so they can actually do much better research on people than if they had just independent people. It also is much quicker to get to a reject the null. So this test is wonderful, but it typically requires advanced planning. You cannot just simply throw anything out there and say, well, let's just pair it together for the heck of it. The data has to be paired originally. You have to know what goes with what to begin with. There are times where researchers will purposely pair unrelated people. What they do is they'll get a profile on each person, find out so much about each person, and then they'll find the closest match they could. Kind of a computer dating thing, you might say. They don't have to tell you who your partner is because it doesn't matter. And then what they'll do is one group will be in the control group and one will be in the experimental group, and the partners will be split up not knowing who their partner is. If one partner drops out of the study for whatever reason, the other partner is also out because otherwise you'd have nothing to compare the data to. They may let you finish it out because they might run other tests, but for the purpose of the paired samples, they can't use you. And they figure you two are close enough in your metabolism and habits and stuff that we can randomly put you in one group and it really shouldn't matter. The example I have here would be, what if we asked 2 appraisers to look at homes and appraise them? Now, what values did they put on these homes? Appraiser 1 appraised the first term for $135,000. Appraiser 2 appraised the same home for $128,000. We do that for 10 different homes. Notice, if I just said, you appraise 10, you appraise 10, problem is one can appraise 10 at the beach, the other can appraise 10 in the slums. That doesn't help us much. What makes this such a valuable test is they had to appraise these same 10 homes, preferably on the same day, because you don't want one to go through when the house is disheveled and one when it's immaculate, or one when it's pouring outside and you could see rain leaking through the roof, and the other one when it's gorgeous outside and you don't notice those things. So just to be fair, they should go on the same day, even if it's hours apart, so that their results are similar, and it's also based on the same comps, the same comparisons in the neighborhood. And in this particular one, we saw with, I think, 9 of the 10 went in the same direction, where appraiser 1 was higher than appraiser 2. The p-value for this one, we don't expect one to be the higher than the other specifically, so we do a two-tailed test, and the p-value for this turns out to be 0.0092. Now realize the mean for the first group and the mean for the second group are not that far apart. And if I ran these 2 columns in the independent samples, the p-value would be extremely large. But because I'm able to pair them up, I have a p-value that's very, very small, and I can then conclude, yes, there is clearly a difference in the appraisals you get on the same homes from appraiser 1 and appraiser 2. So when we have 2 samples to test, we did t-tests, whether it was paired samples or independent samples. But what if we have 3 or more groups? Then what? Well, suppose we had 5 groups. I'll call them A through E. If we were using those two sample tests, we would have to do a test comparing A to B, then A to C, then A to D, and so on. In the end, we would have to conduct 10 separate t-tests in order to address all the differences. Doing 10 separate t-tests, each one incurs a probability of a type 1 error, a probability of rejecting the null hypothesis by mistake, based on whatever the significance level is. When you do that 10 times, you're not guaranteeing, but you've strongly increased the chances that you're going to reject the null by mistake on one of them. Just by the law of large numbers, it's bound to happen. You keep taking more and more comparisons, it's very likely to happen. So we're almost guaranteeing that we're going to get a false result here. Kind of put it in perspective, imagine you're in a large classroom, say about 50 students, 40 students, something like that. And teacher makes an offer and says, roll these 2 dice. If you roll double 6, you lose. Anything else, you win. But double 6, you lose. What do you win? Guaranteed A in the course. You can leave right now. What do you lose? Guaranteed F. You're dismissed from the university. Okay. Is it worth the risk? Now, individually, you might go, well, gee, the likelihood of rolling a double 6, there's 36 possible dice rolls. 6 times 6 is 36. There's 36 possible dice rolls, 35 of which are good outcomes. Only 1 is bad. So that means there's a 1 in 36 chance I lose. That's only about 3%. That's great odds. Well, would you risk it? 97% chance it's going to work out in your favor. Would you take the chance? Sounds like there's nothing to lose, but there's a lot to lose. There's a lot at stake here. So let's suppose that each person in the class decides, hey, 97% chance, my God, I'd be crazy not to. Well, if something has the odds of 1 in 36 of going wrong, and 40 or 50 students in the class take this risk, would it surprise you if 1 or 2 roll double 6s? We're almost assuring it's going to happen. It's not a guarantee. You can have 100 people and it turns out nobody rolls it. On the other hand, you can have 100 people and 5 or 6 people roll it. But when the odds are 1 in 36 that something's going to go wrong, someone's going to lose, and you have 40 or 50 people doing it, you're almost assuring 1 or 2 people will lose. And those people will reflect and go, my God, how did I lose? The odds were in my favor. I had a 97% chance of winning. And taken individually, they're absolutely right. But when you throw the whole class together and each person individually has a 3% chance of losing and there's a lot of people who try it, suddenly the odds of somebody losing grows to over 90%. Well, same thing here. I'm comparing groups A to B, A to C, and so on. Each time I do a comparison, there may be only a 5% chance of a type 1 error if that's my significance level. Maybe it's 10% if I made it higher. But you do enough of these tests, and that overall chance of a type 1 error just grows and grows and grows. So what do? Well, we turn to the analysis of variance, also known affectionately as ANOVA. ANOVA allows us to compare 3 or more groups at the same time. It uses a technique whereby it's looking at the spread of the data from group to group to group and the spread of the data overall to see whether or not there's a difference. Like maybe the reason why our data, the overall data is so spread out is because one group is at the low end and one's in the middle and one's in the high, and when we merge them together, we get data all over the place. Or maybe the spread of the data is all over the place because each group is all over the place, put it together, and it's still all over the place. So that's what you're really looking for, whether or not it's contributed to by groups being all separated, or whether it's just that each group already looks like that, so no big surprise. ANOVA is going to look at that. So it's literally looking at the spread, and it doesn't matter how many groups I have. The Excel file we have here is rigged to only handle 5 groups, but there's no limit to how many you can put in there. And the great thing about this, too, is that after it's done the analysis on the 3 or more groups that you're comparing, if anything is significant, it will then turn around and tell you what it is. So essentially, it will perform the t-tests for you at once, but you basically ignore that if it turns out that the ANOVA was not significant to begin with. because you don't want to say, yes, we rejected the null on one of those little paired t-tests when it turns out that you never would have gotten there in the first place and shouldn't have gotten there except for the fact that you rejected the null on the ANOVA to begin with. So let's compare it. In this case, suppose I had a group students tested on a specific topic. They studied for this quiz on a few concepts, and 1/3 of the class I give them these questions in true-false form addressing these concepts. Another group I give multiple choice with 4 responses. Another group I give fill-in-the-blanks. On the same exact concepts, just different formats. Now, a fill-in-the-blank requires you have this stuff in your head memorized. Multiple choice you can guess your way, and true-false you can guess your way with even greater success since there's only 2 chances in this one. Well, anyway, you load the data in there. The first table, the summary table, just tells us there were 6, and the averages were 18 out of 20, 16 out of 20, and 13 out of 20. Then it creates an ANOVA table. I would rather not go into all the detail. SS is sum of squares, DF is degree of freedom, MS is mean square, F is Fisher. So it's doing its calculations, which for some of you using a book, you might want to look at this for verification that you're doing it right. The table below, though, says here's the actual hypothesis. You don't have to worry about upper tail, lower tail, or two-tailed. This one's already done for you. It's always two-tailed. The null hypothesis in this case is that the mean for group 1 equals the mean for group 2, which equals the mean for group 3, and if there were more groups, we would continue that. The alternate is the opposite of that. The opposite is not that they all don't equal each other. It's just one of them has to be different for you to reject. So the alternate is that not all means are equal. You set your significance level. The p-value that was computed was 0.004, which is less than 0.05, so we reject the null and say, yep, there's a difference. Then you go down below, and you go, let's look at where the differences are. And you say, well, let's compare true-false to multiple choice. It was a difference of 2 points on the exam. No significant difference. True-false to fill-in-the-blank, there was a 5-point difference on the scores. That was significant. Multiple choice to fill in was a 3-point difference on the scores. That was significant. So what we see is that the fill-in-the-blanks were significantly lower than the other two. But we really didn't have enough evidence to say that people did better or worse on true, false, and multiple choice. It just wasn't a significant result. But the fill-in-the-blank was significantly lower than the other two. These tests at the bottom, they're referred to as post hoc tests, the post meaning after. So if I had 5 groups, you would have seen all 10 comparisons in there too. So it'll just include all the possible paired comparisons. As I said, even if something says reject the null, means are different, even if it shows that, if the table above did not indicate to reject the null, you're done. If it said do not reject, you're done. Because anything that's down there is just one of those false positives, basically, one of those type 1 errors that you're getting. Well, if we know we're supposed to reject the null, then by all means go down and look at it and see where the differences are and discuss it, write about it, whatever the case may be. So that wraps up Unit 5. We looked at testing 2 samples, whether they be independent or paired, and 3 or more samples with the ANOVA test. So we've figured out ways to analyze data, whether it's in 1 sample, 2 samples, 3 samples, doesn't really matter how many samples there are. And we've looked at means, we've looked at proportions. We looked at situations where our 2 variables are such that one of them is categorical, like exam type, gender, whatever. The other variable is a scale variable, actual score on the quiz, actual SAT score, actual weight, appraised value on houses, and so on. In the next unit, we're going to look at what happens if both variables are categorical. So we're going to address what's called the chi-square test.